Hello everyone, and welcome along to the inaugural Data Renewables and Me webinar. And I'm Alice Lee, and I'm going to be hosting this webinar for today. And just to remind everyone that's joined in, this webinar is going to be recorded and then will be shared on YouTube and the Catapult website afterwards. So if you have enjoyed what you've seen, do feel free to share it around and get everyone involved. So some of you may have been at or may remember that the Catapult hosted their first meetup, the Data Renewables and Me meetup back in February in the Dram Pub in Glasgow. And following the successful meetup, we wanted to organise another one and keep the momentum going. But due to the whole COVID-19 situation, we decided to make this a webinar. So with this webinar, we wanted to get some contrasting views about wind farm control. So we thought we'd bring together a problem provider, owner-operator with access to lots of different data, and a solution provider, an SME that deals with data analytics every day. Bring them together and get the different views about wind farm control. So what is wind farm control? That's not really for me to answer. I'm not the expert, these guys are. So hopefully they'll elaborate a bit more. But in essence, it's optimizing the control of a farm as a power plant, as opposed to optimizing the production from individual turbines. So on the call today, we have Philip Bradstock, the head of scientific computing at Bitbloom, and Anastasios Paprakau, also known as Tassos from Innogy. Sorry if I got the pronunciation wrong there. And David Thompson from the Catapult. So we're going to start the presentations today with an SME that's been involved with some projects at the Catapult already. In particular, they were a finalist in the recent Power Available Hackathon held in the Glasgow Science Centre. Philip Bradstock is the head of scientific computing and co-founder of Bitbloom, delivering software and services for data analytics, scientific computing, and application development to the wind industry. Having developed software for both aeroelastic and wake modeling, Bitbloom know how to model the essential components for wind farm control. Today, Philip is going to be talking about how the different mechanisms of control can work on a wind farm level and touch on some of the simulation work done around this already, as well as potential gains that come from this. Sorry, and I should have mentioned before, all participants that are on the webinar today can use the question and answer function to ask any questions they may have during the webinar, and we'll try and address these at the end of the presentations in general, in whole. So yeah, Philip, I'll give over to yourself.
Okay, thank you. Hi everyone, and good to be talking to you today. Hopefully I just hope to provide a little bit of insight into wind farm control from point of view of an SME and more the modeling side of it. Okay, so firstly, just to introduce ourselves, who are we? So we're an SME, so you might not have heard of us before. We actually come out of the merger of two even smaller companies, Simovation and Lindau Limited. And we provide a range of stuff from software consultancy to operational data analysis consultancy. So on the operational data side, we're doing a lot of SCADA analysis and performance monitoring, yield assessments, and some automated analytics and condition monitoring. And then on our software consultancy side, we're doing quite a lot of modeling in the wind industry. So we're doing aeroelastic modeling and also wake modeling and helping companies with their numerical modeling and software that they incorporate into wind energy and other renewables. And in the crossover of that, we also have various software products, the most well-known of which is SIFT, which is a data analysis and SCADA analysis toolbox and data visualization. So firstly, I just want to give an overview of what wind farm wake losses are to sort of identify the problem before we try and solve it. So when you have operating turbines in a farm, they extract momentum and energy from the wind. And this has the effect that turbines that are then directly downstream of those turbines that are extracting momentum and energy, those will then have less momentum and energy in the wind by a reduction of the wind speed. But it's still generally beneficial to locate our turbines fairly close to each other for things like cable costs and maybe just generally the land you own, or the depth of the seabed, or other environmental factors like that, which means you end up having these wake losses reduce the power in your farm, and the closer they are together, the less power you will have as a collective, or your wake losses will be larger. And so depending on the layout and spacing of your farm, wake losses are typically somewhere in the region of 5 to 20%. On the right here, we have a simulation of a reasonably extreme farm called Lillgrund, where the turbines are just spaced 3 or 4 rotor diameters between them. And so that would be at the upper end of this scale, towards having sort of 20% wake losses. And if you look at the wind farm efficiency, that is the power, the actual power that the wind farm gets as a ratio of the power it would get if there were no wake losses at all, by the according to the wind direction, then it looks something like this. And you'll see there's significant dips in areas like 120 degrees and 300 degrees, where the wind is going along the rows of turbines, essentially. And a key thing in wind farm control really is trying to reduce these dips, so to make that drop in power at those wind directions less severe. But before we go on to wind farm control, I'll just talk a bit about wake modeling and how this is done for mostly for energy assessments at the moment. So when we do wake modeling, usually this is done based on 10-minute average steady state conditions. So if we were to look at the sort of frequency or spectrum of the wind, this graph on the right here called the Van der Hoeven wind spectrum, it depends on where you are in the world, of course, but it generally looks something a bit like this. So you have a peak down at the right here, which is what in layman's term we might call turbulence. So this is the sort of gusts of wind and it changing on a basis of a few seconds. And then at the higher end, we have a lot of content at the sort of daily and weekly level, which you might talk about as climate and weather. Like, it was windy last week, it's not so windy this week, etc. And that leaves this nice spectral gap in the middle here. And so what we do typically with wake modeling is we model at this sort of 10-minute level, and all what we call turbulence, we absorb into that wake modeling and absorb it into some statistics, like standard deviation and so on. Aeroelastic models, by contrast, have to model at the high frequency end and to see all their reaction to the turbulence and so on, and the impact of that on loading. So most commonly used for energy assessments currently are fairly low fidelity wake models called single turbine wake models. And these are ones where the wake of each turbine is modeled individually, and then they're added up somehow to make a farm effect. At the other end of fidelity, we have large eddy simulations, which include stuff like open foam and tools based on open foam. But with those tools, they're mainly used in research because they're too intensive to be used for things like energy assessments or even wind farm control. And there's also some fidelity tools that model the wake of the whole wind farm together, but are less intensive than LES. And Wake Blaster is one example of that. So now I'm going to talk about the main techniques to try and reduce this wake effect, which really is what all wind farm control is about, is reducing these wake losses in a dynamic manner. And so the first one to cover here is induction control. So if we imagine we have an upstream turbine here, the wind is going along this green dotted arrow, and that will be putting a wake onto this downstream turbine, where the sort of red is the central strong bit of the wake, and the yellow a little bit weaker. And left here is typical thrust coefficient and power curve of a turbine, something like that, kind of in a qualitative manner. And so the idea of induction control is, if we reduce the thrust of the upstream turbine. So firstly, I'll just point out that basically the strength of a wake is proportional to the thrust coefficient, or the proportion of momentum you extract from the wind is essentially equal or proportional to the thrust coefficient. So if we can reduce that thrust coefficient, then we'll reduce the strength of the wake. But of course, we can't quite do that for free. Reducing the thrust coefficient will also reduce the power that upstream turbine is getting. But if these turbines are directly in line, and you've got another turbine behind there, then the hope is, by reducing the thrust and power of this upstream turbine, we can gain even more power from the downstream turbine by increasing its incident velocity. As we also have to think about loading, though. It's not everything is just about energy capture. If a turbine is receiving higher loading, that means the turbine will be more expensive to build at the end of the day, and then our cost of energy, the cost of energy is essentially energy capture divided by sort of the loading of your turbine, indicating its eventual cost. So in this scenario here, we've reduced the energy capture of the upstream turbine, but we've also reduced the loading on that upstream turbine. And then we have increased the energy capture of the downstream turbine. And it's not clear or not whether we would increase or decrease the loading of the downstream turbine. Probably the decrease in wake balances out more or less the increase in thrust that turbine will ultimately receive. So the other main technique, which is becoming more and more the most promising technique, really, is called wake steering. So the basic idea here is, if we yaw the upstream turbine to steer the wake away from the downstream turbine based on their relative location relative to the wind. And so again, going back to this base example where we've got this downstream turbine heavily waked by this upstream turbine directly in line with the wind, what we now do is if we yaw the turbine something like this, then due to how the aerodynamics of the rotor works, then this will deflect the wake in this kind of curved manner, slightly to the side of the other turbine. You have to do a fairly strong yaw to deflect it significantly, and so probably with this you're still going to have some waking on this downstream turbine, but maybe you can do it enough to get off the worst. So this would here, so we have a reduction in energy of the upstream turbine due to it not being front onto the wind anymore, and this also ends up being an increase in loading on that rotor as well, an increase in periodic loading. but we're gaining stuff at the downstream turbine. So we're gaining power because the wake isn't so strong on it anymore. And we're probably also reducing the loading. But I made this arrow a bit hollow here because that's not always the case, depending on the situation. If you've got a partial wake like this, you can actually end up increasing the loading. But generally, because wakes have higher turbulence in them, being in a wake is higher loading than not being in a wake. So with this technique here, in this case, you can see a small benefit. But then, if you imagine if this downstream turbine is not actually directly in line, but it's slightly up a little bit, then you would go from being mostly in the wake to almost completely out of the wake with this steering. So depending on the situation, this can be a really beneficial thing to do, actually, and can provide bigger gains than the induction control measured before, which is very much a difficult equation to balance because you're always losing power somewhere and gaining power somewhere else. Just to show this instead of my poor quality PowerPoint diagrams, this is a sort of 10-minute averaged SOFA simulation. So SOFA is a high fidelity wake model tool from NREL in the US. And you can see here, I think these are 0, 10, and 20 degrees. You can see that deflection effect and how it's sort of moving the wake downwards in this bottom plot here. So now that I've sort of mentioned the basic concepts, now I'm going to talk about actually modeling wind farm control and how we do that. So we have to bear in mind the wind is not steady state. At the moment, we've kind of been talking about these 10-minute averages. But if you look at a finer level, you'll see that actually the wake is meandering like this due to sort of large scale turbulence eddies and so on. And that means that rather than modeling at this 10-minute level to sort of accurately model our wind farm control and see the effects of that, based on the fact that we're looking to operate our controller probably at a sort of smaller time scale than 10 minutes as well. Wind farm control, we want to sort of capture the main parts of this turbulence and these sort of large scale eddies and model this meandering as opposed to this sort of time average view, which has those statistics incorporated into it. And also we have to think about the sort of transfer of information, if you like. If you consider these two turbines, say 600 meters apart, it's fairly typical. The wind is at 10 meters per second. So you're talking about 60 seconds for certain sort of air particles, if you like, to go from the upstream turbine to the downstream one. And therefore the sort of time lag in this information or time lag of the wind passing from one turbine to the other, and incorporating that into your modeling is a tricky thing to think about and has to be considered rather than thinking of things in steady state.
Just to let you know, Philip, that's time like 50 minutes up. So if you do want to just try and wrap up, that'd be...
Yep. Okay.
Thanks.
Yeah. This is final slide now. So this is just a sort of basic diagram of how you might want to model your wind farm controller. So you've got a controller here, a simple turbine model producing your wakes. Your wake model needs to include this sort of meandering effect with sort of large eddy 4D turbulence. 4D because it needs to be time as well as downstream distance because turbulence evolves as it goes. And then you've got other turbines, downstream turbines, sort of picking up this and sending information back to the controller, like their wind speed and turbulence and so on. And just on the left here are some examples of models in the industry that are doing this at the moment. So most notably, I think Floris from NREL They have a range of low and mid fidelity tools for modeling the wakes, and there's also long sim from DMVGL, and that's it. Just a little figure at the bottom saying we could also use machine learning. We should probably get excited about that in a data webinar, to model these wakes, kind of taking farm layout and wind conditions and turbine operation as features, and sort of going into turbine power and turbine wake induction as targets or outputs, just to get people thinking about that. One or two people have done this so far, but it's not really a well explored idea at the moment. And that's it.
Great. Thanks very much, Phil. Very, very interesting indeed. It's great to see how the different mechanisms for wind farm control can work and how they might bring potential different impacts and benefits. Okay, so great. Moving along from our SME view, a kind of solution provider view, we're moving to the owner-operator view. So our next presenter deals with data analytics at operational wind farms around the UK on a daily basis. And is also the technical advisor on the Sparta benchmarking program. Anastasios, also known as Tassos, is a performance analyst at Innogy Renewables, a major owner-operator of wind farms with over 2 gigawatts installed to date and another gigawatt in construction. Innogy are leading the way when it comes to wind farm power, and also showing the industry what can be done with data analytics. So today, Tassos is going to take us through how wind farm control works and operational wind farm, talking about the benefits for an owner-operator based on some of the R&D work in-house. And looking forward, Tassos will touch on how this could be used in a forward-looking manner to plan out wind farms in the future. So Tassos, please do take us away. I think you might still be muted there, Tassos.
I was indeed. Hi all. Thanks, Ali, for introduction. Just give me a second, please. So yes, thanks for the invite, Ali. I will be talking about the wind farm level control from an owner's perspective. I just want to say a few words about my background, which is mainly in engineering. I joined Innogy roughly 4 years ago, and I've been working in the O&M department, where I held a couple of different positions, mainly looking at O&M modeling and O&M strategy and implementation, and more recently, reliability analysis and performance. So a few words about Innogy. As you already mentioned, it's a big distribution system operator and electricity provider with quite a big revenue. For 2018, it was roughly 37 billion euros, and with activities in about 15 countries across Europe. We currently have 43,000 employees and about 23 million customers. And the main segments of the business are grid and infrastructure, retail and renewables. And specifically for renewables, we have assets in offshore wind, onshore wind, solar, hydro, biogas and biomass. This is just a snapshot of our operational fleet. 4 main wind farms in UK waters and another 2 in Germany. I've also included a few projects, so the portfolio, the fleet is expected to grow significantly over the next few years. And I come, as I mentioned earlier, from the asset integrity and performance team. So I want to say a few words about my team. Our main role is to review the SCADA data, vibrational data, and oil and grease data. And we try to identify, to analyze the data and identify any issues we see on our fleet, on our turbines. And we perform a diagnosis, or if we have a failure, we might perform a technical root cause analysis. And we feed all that information to the site teams, that they are responsible for carrying out further investigations if necessary on site. And of course, by working with the site teams, we aim at improving the reliability of our wind farms and the availability of the turbines in order to maximize revenue for the organization. I have a couple of slides describing what wind farm level control means. Philip, I think, explained it quite well, so I'll go through these very, very quickly. So one approach is by pitching the blades, as already Philip explained. And why do we do that? In order to weaken the wakes that the downstream turbines perceive, and effectively by doing that we achieve higher wind speeds for and lower turbulence for the downstream turbines. And a second way of controlling in a more holistic way the wind farm in order to maximize the AEP is by intentionally misaligning the upwind turbines. So the objective of this approach is to redirect the wakes, and as Philip explained again earlier, this is the business as usual case where a downwind turbine is behind the turbine at the front, and it's heavily waked, as you see on this image. But if we intentionally misalign the rotor of the upwind turbine, then we redirect the wake, and the turbine behind it is not as waked as under normal operational conditions. This is a very simple plot. I tried to do a very simple calculation and assess what the benefit would be from a financial point of view for a wind farm. So in this plot, I've assumed a wind farm of 50 turbines, 60 megawatts of rated power, a 40% capacity factor, and a price of £15 per megawatt hour. And assuming that any of these approaches would result in an increase of 0.2% in AEP, that would mean that the project, the wind farm, would perceive 0.2 million pounds of profit, of additional revenue per year. If that increase goes to 2%, then obviously the increased revenue goes even higher, to up to 2 million. This is a very rough calculation, just because I wanted to give people an idea of what such an approach how such an approach translates in terms of revenue for a project, for a wind farm. So the main benefit would be obviously increasing AEP, and the second benefit is the potential in reduction of the fatigue and the extreme loads. This unfortunately is not always the case, but hopefully the sum of loads for the wind farm would be less. For example, in the case of the yaw misalignment, we might see increased loads for the first turbine that we misalign by a high number of degrees, but at the same time reduce the wakes, so the turbines behind it should be perceiving less turbulence, therefore less wakes and less loads. Reduced loads for us as an owner, as an operator, it means that we should be seeing in the future an increased reliability of our wind farms across our fleet, which translates to less failures, less maintenance, less spare parts, therefore a lower OPEX. Another benefit could be that less fatigue for certain components could translate to lifetime extensions. So this is something that we would need to assess at a later stage. And of course, lower loads could also mean leaner design for certain components that should hopefully translate to lower CapEx. Another benefit could be the optimization, the better optimization of the layout by using these holistic control strategies. At the moment, we don't do that. So the layout is designed in the traditional way, if you like, without taking into account such strategies. However, if we did take into account these sort of strategies, we could potentially end up with a denser layout. A denser layout for us means less cables. It means a smaller footprint, and sometimes the footprint is a restriction. So that could be a huge benefit if we could fit more turbines using the same space. I try to list a few technical barriers I could think. This is more of a brainstorming, to be honest. But from my point of view, I try to review the literature and some of the work that has been done, and I realized it became very quickly apparent that all the models that are looking into these sorts of control strategies are quite complex, and it seems that it is quite difficult to validate the output of these models by the means of having experimental actual data. So that could be a problem, that we implement these sort of algorithms and we expect a certain increase in AEP, but we don't achieve that. Another technical barrier is that we would need to continuously maintain and calibrate the pitch and yaw systems and sensors, as these strategies rely heavily on either of these systems. And the same goes with the anemometry. It would have to be calibrated, and it would have to be kept in a good working order in order to perform this strategy, to implement this strategy. Specifically for wind farms that they don't come with these controllers pre-installed, but we do a retrofit. There are some more technical issues to consider. For these turbines, for these wind farms, we would have to upgrade the controller. Of course, for that to happen, we would need full engagement from the OEMs as owners, as operators. We don't have we don't have the permissions, first of all, to do anything with the controller, especially during the period when the wind farm is under warranty. But if even after the warranty period, we wouldn't have the knowledge to do that. So in either case, we need full engagement from the OEMs. And in order to monitor and assess the performance of these strategies, we might need to install additional monitoring equipment. That could be LiDARs, in order to measure the wakes, or it could be strain gauges and accelerometers to make sure that the turbines don't perceive high loads and they don't exceed the designed envelope. And the last one is that we would probably need to adjust the operating conditions for critical components. For example, the yaw brake pressure would have to be adjusted in order to cope with excessive yawing misalignment if that is required. Then if we move on to the implementation phase, some of the risks I try to put together. The very first one I thought was anemometry. Very often we see issues with the anemometry. Of course, we can't avoid that. This is something we will be seeing during the implementation of these strategies, and that could be an issue, a problem. Then another risk is the pitch and the yaw calibration. That would have to be performed across the entire site, and beyond the initial calibration, we would have to make sure that these sensors or the systems do not drift away with time. For example, in some cases, we have observed that the yaw sensors might drift away with time. So this is something that we would have to monitor continuously and correct any issues if we see any. And the last one is that the main components that will perceive an increased duty will be the pitch and the yaw systems, and this might have a knock-on effect on some of the subcomponents of the system, such as, for example, for the yaw system, the pinions, the yaw gearbox, brake calipers, or any other subsystem that experiences very high strain. Another issue to consider here is the additional time that the additional downtime that we will perceive due to technical standbys. A good example of that is a cable unwinding. So if we have increased yaw duty, we might have at the same time increased number of cable unwinding events, and that would cause additional downtime for us. Specifically for the yaw duty, we might also perceive an increased own consumption. A very rough calculation I did was that 35 or 40%, roughly 40% increase in yaw operations could reduce AEP by 0.1%, which is quite significant when you compare it with the benefit we might see from these improved control strategies. Then in the case that we have high loads, we might see a higher failure rate across the fleet, at least for those for those two subsystems that they have an increased duty, such as the pitch system and the yaw system. I have to admit that the loads, the impact on the loads for the turbine, the tower, and the foundation was not exactly clear to me. So there are some concerns about that and what the impact on the foundations could be. And another risk during the implementation phase could be that we have an increased number of failures, and that could affect the way that the strategies work. For example, we might have an upwind turbine that has failed, and therefore this would affect the way we operate the downwind turbines. And few words about the contractual landscape of such improved control strategies, which is probably the biggest barrier at the moment, in my view. I try to split that in two different categories. So the contractual landscape for existing wind farms is slightly different to the new wind farms. I'll start with the new wind farms because things are a bit clearer here. These strategies, I wouldn't expect them to be warranted at the first stage, at least. So they wouldn't go, this extra yield wouldn't be warranted by the OEMs. At the same time, such strategies would add complexity to the existing contracts, to turbine supply agreements and service maintenance agreements. These are quite complex contracts already, and including this sort of improved holistic control strategy would be an added complexity probably. The question would be, how do we capture any additional yield in the contract? And the same goes with my next point. It again refers to the contract. Under which environmental conditions would we include this additional yield into the contract, and under what environmental conditions would we exclude this any additional yield? And it would also make things a bit more complex when it comes to power curve tests. And if we are talking about a retrofit to existing wind farms, the main risk I see is reliability. And the question here is, how do we split that? How do we split this risk between the OEMs and owners? Again, we would need, I imagine, to have an agreement between the two parties and split that risk. And when it comes to warranty for an operational wind farm, if that wind farm is under warranty, then I don't even see it possible to happen. And again, we would need, in any case, a full engagement from the OEM because we would need to upgrade the controller, and this is something we wouldn't be allowed to do. And when it comes to wind farms that they are not 100% owned by one party, but there's shared ownership, in that case, things become a bit more complex because you would need the agreement of all the parties, of all the shareholders involved. And that was it. Thank you.
Okay, thanks a lot, Tassos. Very interesting hearing how you're talking about how the OEMs are involved and integrating with them for the control mitigation. Just to remind people that are on the call, it's great to see some activity in the questions and answers box, but that is just down on your bottom bar, so feel free to click on that, ask a question, and you can also upvote some of the questions that are on there. There's some great ones in there already, and we'll address them after the final presentation. So yes, our final presentation is about some of the work undertaken by the ORI Catapult around wind farm control. In particular, our participation in the Total Control project. So David Thompson has been a mechanical engineer at the ORI Catapult since 2017, and has experience in wind turbine control systems and dynamic modeling. His role involves working closely with organizations to develop and demonstrate and de-risk innovative technologies with the potential to reduce costs and increase safety for the offshore renewables industry. David, if you want to take us away for our final presentation. Thanks.
Okay, hang on, share screen. Okay, can you see that?
Yep, that's coming across great, thanks.
Okay, fine. Right, so I'm going to talk a bit about the the Total Control project and what that covers, and its approach to wind farm control, and this idea of the farm as a power plant. Have a quick look at some of the turbine level control requirements for the farm control, and then a little bit at the end about some of the work that we're doing on wake steering. So Total Control is a 4-year project. We're about halfway through, or just over halfway through. There's 4.9 million euros of funding through Horizon 2020, which is split between the organisations you can see on the right there. So, goal of the project is to move away from the individual optimization of wind turbines to optimization of the plant operating as a whole. So 3 points to that are maximizing yield, so generating as much power as possible, reducing operating costs through reducing loads, mainly fatigue, on major components of the wind turbine, and enhancing capability. So this is ancillary services, usually. Things like grid frequency support and things like that. So now, Philip mentioned the Van der Hoeven spectrum before in his presentation, and how different features of the wind are split across different sort of time scales. This is sort of an expansion of that. So that column in the middle is really a list of physical features of the wind farm and operator decisions that kind of go along with that, and rough timescales on the left-hand side. So at the longest timescales, you have things like O&M scheduling, which happens on year, month sort of schedules, getting ships out. It's quite a slow process, so things are planned far ahead. With farm control, we're looking at optimizing the operation of the wind farm to sort of coincide with this sort of operation. So part of the Total Control project has cost modeling of how these O&M scheduling events can coincide with how load is balanced across the wind farm. So, and that load is balanced across the wind farm by doing the things that the two presenters before have talked about, things like yaw wake steering and induction control. So the balance here is adapting the market conditions to environmental conditions and the power generated. So moving down there a bit, when the sort of faster timescales, we're going towards things like the turbine to turbine flow times. So this is the amount of time it takes for the wind to flow from one turbine to another. So it's like the length of that wake, which is about of the order of 100 seconds or so for a large wind farm, with widely spaced turbines. So when you get to lower times, to lower time periods than that, seconds, milliseconds, then you're getting beyond what you can actively control with yaw and induction control. So just simply because the speed that you can yaw your turbine is not fast enough to create an effect at these timescales. So we're looking at different farm control, different individual turbine control operations that can be done at those speeds. So primary frequency response obviously is not can be at the millisecond level, so it needs to be done in a way that can respond to that quickly. Okay, right, so I'll move on. Now, so just to outline the sort of thing that's happening at these longer timescales. So increasing plant power operated by yawing and induction control, the same as what I was talking about before. The task of the farm controller here will be to pick which turbines to do this with. Now, traditionally this is sort of explained as the front row of the turbine, the front row of the wind farm, even yawing to increase the power output of the turbines behind it. Now, the farm control needs to be a bit more advanced than that. You're selecting the turbines to yaw, control induction, things like that, by things like the turbine history, inspection reports, and also the current operating point of the turbine. So if some turbines in the farm are generating more power than others, for example, they might be better candidates to reduce the power off on a farm level. In the future, this sort of operation might be expanded to include things like condition monitoring in real time, and this will allow turbines with more severe load histories, or turbines which condition monitoring think are likely to experience a failure soon, to have the loads reduced in advance of any failure happening. These long timescales will also include things like down rating in response to electricity markets and tertiary ancillary services, so, which are happening on hours, days of timescales. Okay, so moving on a bit to the shorter timescales now. So as I said before, we're looking at things that are happening on the sort of less than a minute sort of timescales. So we can still reduce loads by yawing induction control, but the magnitude and the turbine select, the magnitude of that load reduction and the turbines at which that's happening with, we're more likely to be driven by local measurements. That might be through the turbine operating point itself. It might be through a LiDAR on the turbine itself. But the point is that it's not done on this lower frequency level that we were talking about before. So you have these sort of things happening on the minutes and seconds response, and then also the turbine itself, individual turbines will provide these primary ancillary services. So, well, the farm will provide the services, but the selection is done to the turbine level. So things like fast frequency response and voltage support. Now, so also want to take a minute here to just talk about some of the work that we're doing on individual turbine control. I know this is an event for farm control, but total control does have a few projects for a few parts of the project for individual turbine control. So we are looking at LiDAR feed-forward control. So our turbine at Levenmouth, which you can see in the photo there, currently has 2 LiDARs fitted to it. One facing forwards through the rotor, and one facing backwards at the wake. The forward-facing one we're going to use to provide feed-forward control and test that on the turbine at Levenmouth. This is some of the work which is ongoing at the moment. Testing is due to happen this summer, but we'll see about that. Depends on the current situation and everything. We're also looking at testing more advanced individual pitch control. So we're looking at using the tower sensors rather than blade sensors to influence that, and we'll test that at Leavenworth too. Okay, so moving on. This is something that should be happening right now, but has been delayed a little bit because I can't get to site. Now we are going to do a wake measurement campaign at Leavenworth. This is you can see the LiDAR there, fitted to the gantry at the back of the Leavenworth turbine. That's going to face backwards and look at the wake as it leaves the rotor. We're going to do a series of tests with deliberately introducing a yaw error, and we can use the anemometers fitted to the turbine, wind vanes, and then the MET mast, which is situated a few hundred meters away from the turbine, to work out these yaw errors. And we're going to measure a deficit profile and the center line of the wake as it bends away from the back of the turbine. And we're going to look, I've said 1/2 to 2 diameters downwind, but I think we're going to about 500 meters, which is a bit more than that. So obviously the aim of this is to evaluate the wake steering strategies, which will be used in wind farm control. It will also, the purpose of that is to validate the flow models that we have, computational models, and eventually part of the total control projects will be tested at Billigrund, which is operated by Vattenfall. Yeah, so at the moment this should be happening in May, but it's been delayed a bit. We're currently looking at ways of doing this remotely, so we should still be able to do it soon, but that's work in progress. Okay, and that's all I have to talk about.
Great. Much, David. It was really interesting. It was only a small part of your presentation, but talking about how you might be able to use condition monitoring in the future to reduce load on turbines that are maybe more susceptible to damage. So it's very good. Thanks a lot.
Yeah, so I just switch to add to that. Important part of this farm control, and I think Adam Stocks asked a question about it. I've not read the whole thing yet. The important thing about farm control is that we're asking turbines to do things that they are capable of doing, and condition monitoring will be an important part of that, I think.
Nice. So yeah, we're going to open up to the question and answers, and there's quite a few there already, and we're just going to run over about extra 10 minutes, I think, just to allow some of these to get answers. Please do go on there, upvote, and ask some more. Start of a easy one-line one. I think Tassos, you might be best to answer this, although Philip, you might be able to give a good view on it as well. Quite simply, are any OEMs offering this? Adam Stock has already given an indication to an answer by Siemens might be offering a yaw control method, but in your experience, have you worked with the OEMs much and some of the solutions that they're offering?
Yeah, so the answer is no. We haven't had any OEMs offering this to Innogy, at least. Not yet. As far as I know, OEMs do work on that, but we haven't been offered this functionality yet.
It's good to hear. There's another one around the asymmetric loading, but I think that might have been answered already.
I try to answer that.
Yeah. Do you mind just for everyone that might not be reading along the question, giving a quick summary about the asymmetric loading and how that might be affecting the turbines? So
probably Philip might have a better view on that, because I would be talking based on the literature I read, as I'm not a specialist. But yeah, as far as I know, yeah. Sorry.
No, I was going to say, are they asking about asymmetric loading on the turbine doing the yawing or the downwind turbine?
I try to
the downwind.
Yeah. Okay.
Yeah. Yeah. If I just say, oh, sorry, Tassos, carry on.
No, carry on, please.
Yeah, I was just going to say, so my understanding is it's complex, right? So if we forget about wake meandering for a moment, then the question is correct in that a partial wake that doesn't move on a downstream turbine is worse for that turbine in loading than a wake that's directly centered on, because you'll both have the increased turbulence and you'll have this sort of periodic loading or sort of asymmetric, as you point out, and that will be higher loading. But when we start to consider that actually the wake is meandering, then it starts to be more complex. So if you do have a turbine that is directly downstream and full wake in at a 10-minute level, then with the wake meandering, in fact at the sort of 1 second level, that turbine is going in and out of the wake, in and out of the wake, and will have that kind of asymmetric loading, sometimes on one side of the rotor, sometimes on the other side of the rotor anyway. Basically it's complex, but if you do try and steer the wake away from the downstream turbine, then in the sort of wake meandering situation, you'll have sometimes the turbine completely free of the wake and then sometimes partially loaded, which I think is a lower loading situation than sometimes having the turbine partially waked and sometimes sort of fully waked. So yeah, I think my answer is it's kind of complex and has to be modeled well, and an uncertainty in the modeling is sort of key, or well, having low uncertainty in the modeling is key to answering that question accurately.
Okay, thanks a lot. So there's a couple of questions on here, kind of relatively asking just for a little bit more of elaboration about why the pitch technique seems to be not as sought after as the yawing technique. I think you both kind of alluded to it in your presentations, but you might be able to elaborate a bit more on why people are looking at more of the yaw technique than so much the pitch. Tassos, if you want to start with your view on that.
Yeah. My answer would be very short. My understanding is that yaw technique is more promising. So from modeling results I've seen, usually yaw approaches provide a higher AEP increase compared to the pitch solutions.
Okay. And Philip, I don't know if you have anything to comment on that as well.
Yeah, I agree basically. I think with the induction control, like the reduction in power you have for the upwind turbine is barely made up for by the increase in power in the downstream turbine. I think someone asked about whether you would employ it for all wind speeds, and I'm not completely sure, but my understanding is that's most useful sort of below rated, or sort of just below rated, if you were. So where you still have a high thrust coefficient, but the power curve is quite steep. So if you're halving the wind speed of the downstream turbine, that's at least quartering the power, if not, say, taking something like an eighth of the power, given power is sort of wind speed cubed, proportional to wind speed cubed. So yeah, I think the gains through induction control are very marginal, and therefore the wake steering has been seen as more promising.
Good answer. Thanks very much. So we're running out of time, but it would be interesting just to go around and quickly to hear from each presenter what is the biggest benefit that could be gained from wind control, and what is the main limitation in that benefit being implemented now. So what is really stopping that being implemented right now? I don't know if David, you want to start us off with that?
Okay, the biggest benefit would be a reduction in the cost of energy. All of the things we've talked about are increase in power output, decrease in operational costs through reduction in loads and ancillary services. All of these things will decrease the cost of energy.
And what's the main limitation in that being implemented, in wind farm control being implemented right now?
I don't know. What do you think? The as far as I'm aware, there's not much testing that's been done in the field for real wind farms. Well, I've not seen any. Maybe I've not looked hard enough. I've not seen any literature on that yet.
Okay. And Tassos, the same question to you: the major benefit and the main limitations.
So yeah, the main benefit, I totally agree with David. The main benefit would be lower cost of energy, lower LCOE. And regarding the barriers, I think it's the willingness to share IEP. I think that summarizes everything.
Okay. Yeah, I think we see that a lot in terms of the data sphere in renewables and just in general in industries. Is a lot of fears about sharing data, sharing IP solutions. So that makes sense. And Philip, I guess in addition to increased AEP, what is another benefit that you'll be able to get? Is the next kind of top benefit? And then again, what are those limitations? Any other limitations you would say?
Yeah, well, in terms of the benefit, I'm sort of aligned with David and Tassos. It's reduced cost of energy. And there's two parts to that. There's the increased power output you're hoping for, and potentially also you can reduce cost of energy on the loading side. The loading side, it's slightly harder to realize because that means either sort of you've got to go to the point where you can change turbine design, or you're talking about extending the life beyond its typical 20 years, which I think generally is not how wind farms are financed. They don't think about that bit upfront so much, yeah, ultimately it comes down to cost of energy, and that's the benefit. In terms of the main barriers to implementation, I think we need more real world examples that this can work. I think that the research has shown you through many simulations that yes, we can get an increase in AEP here, but there's uncertainties in part of the modeling, like weak meandering that I've talked about, and various other things for the relatively small gains we're talking about, which is kind of 1% AEP or something like this. Ultimately 1% means millions, but yeah, it's relatively small compared to the modeling uncertainty. So I think we need more sort of real wind farms where this is implemented as a trial. I think it's been done a few times in NREL in Colorado in the States. They've done a few real field experiments and shown improvements in energy output, but I think we need more of that. And once that's more established, we'll have more OEMs offering it or third-party solutions. Yeah.
Okay, great. That seems like a good way to kind of round everything up. And there's a call there for more people to go out and show that this works, and more wind farms to take on board these solutions and try them out, try these innovative solutions out, show that they can work and start to reap the benefits from that. So just like to thank our presenters again for their great presentations today. It's very interesting. And thank everyone that's joined into the call today for joining in the first Data Renewables and Me webinar. And hopefully we can run a similar webinar in the future, or maybe a face-to-face one, like we did with our first meetup.